Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how you can predict whether or not what kind of decay an element or a nuclide is going to go over or go through. So in this example I have three examples I'm going to go over, and we're going to predict whether each nuclide is more likely to decay via beta decay or positron emission. And this is all going to come down to the ratio of its neutrons to the ratio to its protons. So that is a ratio that's used if you have a table. I don't have one with me, but if you have one in front of you, you should have like a stability table, the island of stability, or the valley of stability is what it's called, where you can see according to the ratio, you can see if it falls within that island or that valley of stability, then your neutron to proton ratio is okay. But if that neutron proton ratio is too high, then that element is going to have to undergo beta decay to kind of get it closer to the island of stability or that valley of stability. Or if the ratio is too low, then it's probably going to undergo electron emission or positron capture, or electron capture and positron emission. Sorry, I got those mixed up. In order to get its ratio higher, to get to that stable range where it's located. So, so let's go over these examples. So magnesium 28. So 28 is the mass number. So if we look up the the atomic number is 12. So 12, 28 minus 12 gives us 16. So that gives us 16 neutrons over 12 protons, and that's going to give us a ratio of 1.33. And if you look on that table of the island of stability, or that valley of stability, you'll see that for 12 protons, it should be a 1-to-1 ratio, or very close to 1-to-1 ratio. And so this is too high. So we have too many neutrons than protons. So what's going to happen is this is going to have to undergo a beta decay, where an electron is emitted, and that neutron, one of the neutrons, becomes a proton, so it's going to lower that ratio. So this would be more likely to go over, have a beta decay. And you can also see that by the fact, if you look at the periodic table, the average atomic mass is around 24. 28 is definitely higher than 24, so that's another giveaway that this isotope, this nuclide, is too heavy. So it's going to undergo beta decay to kind of lower this ratio. Some neutrons are going to have to become some protons. Okay, so what about magnesium 22? So same element. So here it's going to be 12. If we subtract 12, that's going to be 10. So 10 over 12. So we have 10 neutrons over 12 protons. And if we calculate that, that's going to become 0.83. And so now it's too low. So again, so the NZ ratio is too low. Now we need to bring it up. And so either it can go through the positron emission or electron capture. Either of those is going to change, is going to raise this ratio of neutrons to protons. In this case, either one would work, but I believe, let me double check, positron emission. So positron emission is the only one that we observe, but electron capture would have the same effect. So again, positron emission, a proton emits a positron, a positive electron, and that proton becomes a neutron. So you lose a proton, you gain a neutron, so you're raising the ratio. So that's most likely going to happen for this one. And what about molybdenum 102? So again, we've got to look up the atomic number of molybdenum. So we look up molybdenum really quick. Where is MO? There it is, number 42. So this has 42 protons. Okay, and therefore we subtract 42. That's going to be 60 neutrons. So the ratio here is going to be 1.43. Okay, so this looks high, but according to the valley of stability, that map where we're comparing the ratio, the number of protons and neutrons with the table. So if we look in that table of stability, you will find that the ratio is closer, it's going to be about 1.3. So for 1.3, that would be stable. If we were at like 1.3 at this protons, for this number of protons, 1.3 would be stable, but this is still too high. So again, this one's going to have to undergo beta emission. So this one was positron capture, or positron emission, sorry. Keep screwing those up. Positron emission, okay. And this one's going to undergo beta decay, okay. And again, you could tell by the fact that, wait, did I get this right? Hold on a second. This should be 102. Okay, yeah. So again, you could tell if you compare the average atomic mass to this was the average atomic mass about 95. So again, this is a much higher mass number or atomic mass than the average atomic mass given. So that's another giveaway that this is going to be too heavy. So again, beta decay is what this is going to go through. So beta decay for this one, positron emission, and then beta decay. So I hope that helps. If you like this video, please like, share, subscribe, hit the notification bell, and put a comment in the comment section. Thank you for joining me, and I'll see you next time.